So let's look at the transition from a solid state to a gaseous state. Here on the left-hand side of this image, we have water molecules in a solid state. Lots of hydrogen bonds. The molecules are vibrating. In fact, if you sort of touch a table that you're looking at right now, you might be sitting at, or the desk you're sitting at, even though it appears solid, the molecules are making up that table are vibrating, but vibrating at a very slow speed. They vibrate, but they basically stay in position. Then what happens if we start to add kinetic energy to it, increase the amount of kinetic energy, those molecules are going to start to vibrate quicker. They're going to vibrate, they're going to move more freely, and bonds are going to start to be broken. Those hydrogen bonds that are holding those molecules together. We increase the amount of energy that we're adding to that system. We increase the heat. We're going to add more kinetic energy into the system, and now we see that all bonds are broken. There are no longer any hydrogen bonds holding individual molecules together, and now we have that water molecule traveling in a gaseous state. We have no bonds, and now we have a gas. We can work back the other way. We start to remove heat, remove that kinetic energy, and we're going to slow down that movement of those molecules. So we add heat to a solid, we have melting. We add heat to liquid, we have boiling. We remove heat from a liquid, we have freezing. We remove heat from a gas, we have condensation. The next thing we should look at is look at the heat capacity of water. What heat capacity is, it's the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. If you look at this chart here, the heat capacity of some common substances, we see that water, pure water, has a pretty high heat capacity, one of the highest of all known substances, higher than granite, higher than acetone, higher than gasoline. A high heat capacity means that a substance, in this case water, can gain or lose large quantities of heat with only a small change in energy. So there's a large either input or output of energy, but the overall temperature doesn't change that much. A low heat capacity, on the other hand, means that you gain or lose large quantities of heat with a larger and often quick change in temperature. So really an example is looking at the beach once again. Imagine you go to the beach, it's a hot, sunny day. The sand heats up very, very quickly because it has a low heat capacity. It only requires about 0.2 calories of energy to raise a gram of sand 1 degree in temperature. Water, though, heats up much more slowly. It has this high heat capacity, and that's because it takes a lot more energy to increase the kinetic energy to break these hydrogen bonds that hold the water molecules together. So you need to add more heat or more kinetic energy to really truly raise up the temperature of the water. That's why on a hot sunny day, hot on the sand, but the water still is fairly cool. So water can absorb or release large amounts of heat while changing relatively little in temperature. And this is a really important thing. It means that it takes a lot of time for a large body of water to either heat up or for it to cool down. So we maintain almost a relatively fairly consistent temperature in a body of water over a certain period of time. This is really important if you're an organism that wants to live in the ocean. You're not experiencing wide-ranging fluctuations in temperature from daytime to nighttime. You're living in a state which has really relatively fairly consistent temperature conditions. And once again, this has to do with the fact that water has a high heat capacity. So when water undergoes a change of state, when it transforms from, let's say, it solidifies, freezes from a liquid to a solid, or it melts from a solid to liquid, what we see is that there has to be large amounts of heat either absorbed or released. And this heat here, this heat that's either absorbed or released, is known as the water's latent heat. Why do we use the word latent? Latent just means hidden. We don't see it, but it's there. And it's being transferred within the system that this water is in. It's being transferred as water goes from being a solid to liquid, or we see movement as it goes from being liquid to a solid. So let's take a look at what happens to water when it undergoes a change of state when heat is absorbed or released. And we're going to start off with this little diagram right here, and you'll see there's a whole bunch of different phrases on here: latent heat of vaporization, latent heat of fusion. We're going to work through this diagram step by step by step over the next few slides. So let's start where the yellow arrow is pointing here. We have a solid block of ice. Remember that in a solid, all the hydrogen bonds between water molecules have formed. we're going to deal with about 1 gram of ice. Remember, once again, the definition of heat capacity involves what it takes to raise the temperature of a 1 gram of substance by 1 degree. And what we'll see is to start to break the bonds, the latent heat of melting, the energy required to break the bonds, we need to add 20 calories of heat. And that's going to take the temperature, it's going to increase the temperature of that body of ice to 0 degrees Celsius, and we reach point A. So at point A, we haven't completely melted all the ice. This is where ice begins to start to melt. In order to go from point A to point B to completely melt that 1 gram of ice, we need to add 80 more calories of heat energy. We add 80 more calories of heat energy. The ice, that 1 gram block of ice now has completely melted, and we reached point B. The latent heat of fusion refers to what the energy requirement is needed to move from a solid to a liquid. And remember, once again, latent just means hidden. We continue to add energy to the system, that heat, that kinetic energy, and we start to move from where we have completely melted that block of ice, that 1 gram block of ice, and we move up to point C. So we keep continuing to add heat energy. We keep starting to break those hydrogen bonds, and the actual molecules start to vibrate faster and faster. So if we go from point C to D, to go from just starting to boil water to get that water to complete boil where everything is turning, undergoing a phase change into steam or into vapor, what we see is it takes another 540 calories to go from the yellow arrow to the pink arrow, to go from C to D. This is the energy needed to break all the bonds that are holding that water together, all the bonds, hydrogen bonds between individual water molecules. This is known as the latent heat of vaporization. So to summarize, to take something that's ice, let's say to take a gram of ice and to completely melt it, to break all or start to break the hydrogen bonds that are in that solid, we have to add 80 calories of heat energy. This is known as the latent heat of melting. Then to take that water that we make, that liquid that we make, and completely turn it into vapor, into a gas, we have to add another 540 calories of energy, of kinetic energy. So that's the latent heat of evaporization. If we want to move the opposite way, if we want to take a gas and condense it to form a liquid, then we actually have to take away 540 calories. And once again, if we want to go from a liquid to a solid, we have to remove 800 calories, or not 800, sorry, 80 calories during that process of freezing. And once again, what we're doing here is we're creating hydrogen bonds and we're breaking hydrogen bonds. Now, one thing to remember that so far we've been talking about water, fresh water, pure water, and we're looking at the ocean, we're looking at seawater. And we know that seawater is probably about 96.5% pure water and about 3.5% dissolved solids. What we see is the presence of these dissolved solids actually changes where water freezes and where water is going to actually boil. Most importantly, we see that salt reduces the freezing point of water to below 0 degrees Celsius. The freezing point of seawater is minus 0.19 degrees Celsius. So you can actually freeze water. You can have liquid water below a temperature of 0 degrees as long as you have salts dissolved in it, enough salts. Solids also change, the presence of solids within the water also change the thermal characteristics by lowering latent heats of vaporization, latent heats of fusion by about 4%. So the fact that water has a high heat capacity is actually important in terms of the globe and how heat is distributed towards the globe. We'll see in subsequent lectures that there is an uneven heating of the world's oceans due to the way the sun hits the earth at particular locations. But because water has such a high heat capacity, because it takes a lot to either raise its temperature or lower its temperature, it's really important in helping to moderate temperature changes on the globe. It helps maintain bearable temperatures on the earth. So lots of sun will hit the ocean, but it isn't really going to heat up very appreciably over a short period of time. So the ocean, the fact that water has, even salt water has a high heat capacity, helps maintain livable conditions on the planet. So if we take a couple minutes and look at how temperatures are sort of globally, we see that there's a lack of heat at the polar regions, North Pole and the South Pole. Usually things are hotter around the tropics. So one of the questions you might ask yourself is, why doesn't the ocean freeze solid at the poles, boil away at the equator? And once again, it's because of that high heat capacity. We also see a transfer through both oceanic circulation and atmospheric circulation of huge amounts of heat away from the tropics and towards the pole. And that helps maintain this net energy transport, helps to balance temperatures out, balance sort of areas where we have net heat loss on the planet and net heat gain on the planet. And we'll talk more about this in subsequent lectures. So at this moment, let's take a quick review and see what we've learned about water so far. We know that water is a molecule. It consists of 2 hydrogen atoms and 1 oxygen atom. Water has a unique geometry because of the size of the oxygen molecule in comparison to the size of the hydrogen molecules. We see that there's sort of this 105-degree angle between where the 2 hydrogen atoms are attached to the oxygen atom, and they're covalently bound. They're sharing electrons. And we know that water is a polar molecule. It has a positive end and a negative end, and that it binds together binds together to other water molecules via hydrogen bonding. Other things that we can say about water that we've learned to this point, that it's easily able to dissolve substances. It's known as a universal solvent. It can exist on the earth as both a solid, liquid, and gas. This is very unique. It has a high melting point and a freezing point of 0 degrees Celsius, very different from other substances. Most importantly, it has a very high heat capacity. It takes what it takes to raise a gram of water by 1 degree. And it also helps to moderate global temperatures, the fact that it does have a high heat capacity. Now let's answer the age-old question, why does ice float? Ice is a solid. Why does it float in water? When other solids, you put them in the water, they sink. Generally, as a substance gets colder, it becomes denser. So why does ice float? And we're going to look at this over the next couple of slides. How does the temperature of water affect its density? And we see once again this is very unique behavior of water. What we are looking at here is a density curve. We're comparing density against temperature. And usually when you look at a density curve, what you'll see is a straight line. Instead here, what we see is a curved line. And once again, this is something that's unique to water. So let's imagine that we take a bottle of water and we stick it in the freezer. We want to cool it down. So we're going to start at point A. And let's say this bottle of water is at room temperature. It's at 20 degrees Celsius, and it has at that point a density of a little under 1 gram per cubic meter. The typical density of pure water should be at about 1 gram per cubic centimeter. Sorry, I said cubic meter before. So we're going to start at point A. We're going to stick this bottle of water in the freezer and see what happens. What we should be seeing happening is that as we move from point A to point B, things are starting to get cooler within the freezer. The water is starting to freeze. We're removing heat energy from it. We should start to see that the density is slowly increasing. In fact, it does. We reach let's say the water reaches a temperature of 10 degrees Celsius. We'll see now that the density is slightly greater at 0.9997 grams per cubic centimeter. And then finally we reach point A. Let's say we're at a temperature of just a little bit below 4 degrees Celsius, 3.98 degrees Celsius. And there we see the density of 1 gram per cubic centimeter. So remember that during this time, as we move from point A to point B, we're removing heat energy from the water, and we're starting to form, the water molecules are vibrating slower, and we're starting to form more and more hydrogen bonds. What we're going to look at now, though, is we're going to look at what happens at point B and what happens between point B and point C. At point B, at 3.98 degrees Celsius, water is at its densest. After point B, though, instead of seeing density continue to increase as the temperature of the water drops, what we see is that the water density actually starts to decrease. And when we get to point C, we're at a density of 0.999 grams per cubic centimeter. So what is going on here? What is happening between point B and C? Why do we see this decrease in density instead of what we would expect to be an increase in density? Well, from point B, where we have a liquid, to point C, where we start to see a solid being formed, we're seeing that change in phase. And what's happening is that framework of hydrogen bonds, that hydrogen bonding between individual water molecules is increasing. We're getting more and more hydrogen bonds, and as a result, we're getting this very rigid framework that actually increases in size. So you can kind of see it here in this little diagram. We're going from the liquid with sort of the purpley molecules on the right hand side. We see some of them are starting to join together. We have some hydrogen bonding, but then as we move to a solid, we have all hydrogen bonds have formed, and we have this very rigid structure. And this really rigid structure actually takes up more space than the liquids do. So we still have the same number of molecules, but they're taking up more space as a solid, rigid, crystalline structure than they are as a liquid. So water, actually, the water molecule at this point is starting to expand. It's this fact that as water turns into a solid, as those hydrogen bonds form, that the structure actually expands. And this is why if you stick something in the freezer, especially let's say water in a glass bottle, the glass bottle will sometimes shatter because as water freezes, it expands up by 9%. So it increases the space that it's taking up. So now we have water beginning to form a solid. We have these hydrogen bonds forming between all water molecules. We're creating this rigid structure. We're still removing heat in the process of freezing, the process of creating the solid. So what happens from C to D? Well, we see this change in state. And remember, we don't have solid, we don't have ice forming instantaneously in most cases. There are some extreme cases when this happens, but normally ice doesn't form instantaneously. So we're continuing to remove heat. And what we're seeing is we're continuing to form those hydrogen bonds, and the density continues to decrease. As we continue to move the heat, we continue to see that freezing. Another interesting note here before we kind of finish off on this slide, if you look at water, we see that water freezes over from the top instead of from the bottom. Most liquids will freeze from the bottom up. Water actually freezes from the top on down. So from C to D, we're seeing a decrease in density as all those hydrogen bonds are being formed between all the molecules, and we're developing that complete rigid structure. And at point D, we see that the water has completely frozen, gone from a liquid phase to a solid phase, and now we have a density of 0.917 grams per cubic centimeter. Also, as we change from a liquid to a solid, what we see is that bond angle, that angle between the two hydrogen atoms on a water molecule, changes from 105 degrees to 109 degrees. So we're actually, during the process of freezing, not only creating a more rigid structure with a lot more space in it, but even with this change in the bond angles, we're even forming an even more open structure. And if you look at something, let's say we consider a package of water of 1 centimeter by 1 centimeter by 1 centimeter, so that cubic centimeter of water, we might see that if it's in the liquid state, it contains 27 molecules, water molecules. When it's in a solid state, it only contains 24 molecules. So what's happening here, if you can start to imagine, is that ice as a solid weighs less, it's less dense than water, and therefore, since a solid has a lower density than water does, it's going to, solid as an ice, water is liquid, it's going to actually float on the water. This is why ice floats, because as it freezes, the structure, the framework becomes a lot more open. We have less molecules present than we would have in an equal size particle or parcel of water, and it makes for a solid that's less dense than its liquid form. And this is why ice floats in water. This is why if you have a drink, the ice floats on top of your drink. Water in a solid state is less dense than water in a liquid state.